I want to go into considerably more detail on problem number 7, where really I want to dig into the details on how an exponential function like problem 7 works. So I'm going to show it on a spreadsheet as well as what would be a sufficient handwritten rendering of the graph on the problem on Word. I'll do it there as well. So to start with, we have y equals 1/2 to the x power plus 1. So we want to recall that anything to the 0 power equals 1. And I have a video titled something like the 0 property of exponential functions. So that's a great place to see how and why that rule is the law of the universe, so to speak. But if we have 1/2, one second. Okay, I'm trying to get my Surface Pen to cooperate with us. If we have 1/2 to the 0 power plus 1, and we know that 1/2 to the 0 power just equals 1, then that is equal to 1 plus 1, which would equal 2. And that's what I have here on my spreadsheet. And as an illustration of some details and persnickety nature of how Excel works, I'm going to adjust this just a little bit. Okay, so we also get 2 here, and if you can see this on the video, the sum is equal to the I6, which I'm taking 1/2. You could just plug that into it itself, but I made a cell for 1/2 and just carried it all the way down for demonstration purposes, to the power of, in this case, the cell J or K, to the power of K6, where 0 is, that's our x value, plus 1, and I just carried 1 down everywhere, so I could just add it to that, and then when I drag the formula down, it'll adjust to each cell. Anyway, now let's do the second one, and I did this in the other video, but this is something that can trip people up. If you have 1/2 squared, what that really is 1 squared over 2 squared. So that, of course, 1 times 1, it doesn't matter what power is up here. It could be 999. 1 to the 999 power is still 1, but 2 squared we know is 4. So 1 squared plus 1 is really just 1/4 plus 1, because that's 1 squared over 1 to the 1 squared over 2 squared, which is 4. So it's 1/4. Half of 1/2, if you have 50 cents, half of 50 cents is 1/4, which is 1/4. And there's a pattern you can discern from that too. Clearly this is just going to be 1.25. I think we all know that 1/4 is 0.25. So if I carry that down, and I have the fractions here to the extent that Excel will let me show you all the subsequent fractions, but also you notice that even though that's 1/2, Excel is showing that like it's 2, so we have to make an adjustment since it's rounding. So if I go like this, now it's rounded it to 1/2, and 1/2 is the same thing as 1/2. You can see it's equivalent fraction. And then let's do the next one. If we substitute x for 3, we have y equals 1/2 to the third power plus 1. Well, we know that just equals 1 to the third power over 2 to the third power plus 1. And 2 times 2 is 4, and 4 times 2 equals 8. So that's 1/8 plus 1. And if I drag that down, and drag that down again, you'll see 1 1/8, and it's made it 1.13, and it's actually rounding. So let's see what it would be in decimal. If I have 1 1/8, well, that's a mixed fraction. 8 times 1 is 8, and 8 plus 1 is 9, so it's really, it's an improper fraction. It's 9/8, and that would be equal to dividing 8 into 9. Well, 8 goes into 9 once, right? 8 times 1 is 8. 9 minus 8 is 1. And carry down the 0. 8 still just goes into 10 one time. 8 times 1 is 8. 10 minus 8 is 2. Eight goes into 20 how many times? 8 times 1 is 8. 8 times 2 is 16. So 2. 8 times 2 is 16. And then how many times does... Oh, and then 20 minus 16, excuse me, is going to be 4. And then carry down the 0. How many times does 8 go into 40? I think most of us know that 8 times 5 is 40. And then we're done. That's a terminating decimal. So it should be 1.125. And again, if I adjust this so that it's not rounding, we get 1.125 or 1 1/8. And hopefully you see the pattern. If we went from 1.5 to 1 1/4 to 1 1/8, we're just doubling the denominator each time, the bottom number of the fraction. So 8 times 2 is 16, so we should get 1 1/16. And that makes sense because if I have 1/2 to the fourth power plus 1, well, 2 times 2, which is 2 squared, is 4, and 4 cubed is 8. So that's 2 times 2 times 2 is 8. 8 times 2 is 16, which would be 2 to the fourth power. So 1/16 plus 1. 1/16 plus 1, which is the same thing as 1. Well, 1 1/16. And again, that is a mixed fraction. As an improper fraction, we just multiply the denominator by the whole number. 16 times 1 is 16, plus 1 is 17. So we have 17 over 16. And then we could divide that again if we wish. And actually, you can do this in a calculator much more efficiently. And I'm sure everyone knows this. The trick with a calculator is to have some intuition on what the right answer is. So if you make an error in how you input the numbers on the calculator, you know it's an error and can easily correct it. Otherwise, the calculator may not be your friend. So in any event, let's do this by hand, however. So 16 goes into 17 one time. 16 times 1 is 16. And then 17 minus 16 is 1. Bring down the 0. 16 does not go into 10. So we're going to have to bring this down to 100. Okay, and then how many times does 16 go into 100? Well, 16 times 10 is 160, because that's the rule for multiplying anything by 10. You just add a 0. So what's half of that? Well, half of 100 is 50, and half of 60 is 30. 50 plus 30 is 80, so 16 times 5 is 80. But wait, could we go a little bit higher? So what's another 16? 80 plus 16 is just 10 plus 6. So 80 plus 10 is 90, plus 6 is 96. We're not going to get higher than that, because the difference between 96 and 100 is 4. And that's clearly not enough to fit in a 7th 16. So 16 times 6 is 96. And then 100 minus 96, we just said was 4. Carry down the 0. That's 40. How many times does 16 go into 40? Well, 16 times 1 is 16. 16 times 2 is 32. 16 times 3 is 48. So we know it's 2, not 3. So 16 times 2 is 32. And then 40 minus 32 is 8, because 32 plus 8 is 40. When we carry down the 0, we just said that 16 times 5 is 80. So 1 and 1/8 would be, or 1 and 1/16 would be 1.0625. And let's carry it down. And again, it's rounding, so we got to play with this guy over here. Now, I could go on and on with this, but I think you guys get the pattern here. So also, you'll notice this is what I meant by one of the persnickety challenges of Excel, is I wanted to show the fraction, but it's not letting me do that. Past 1 and 1/8, even though we know that's 1 and 1/16, it's just showing it as 1. It's rounding it up. It's treating it as so minuscule it won't even give me the fraction. So if I just zoom in, I could put that in hand. 1 and 1/16. And then let's just extrapolate. Extrapolate means extending the pattern. Let's extend or extrapolate that pattern. So for the next one, we know it's going to be not 0. I haven't put in the value here, but it's going to be 1, and 16 times 2 is 32. So it's going to be 1 and 1/32. And then for the next one, it's going to be 1 and 1/64. And then the next one, 64 times 2 is 60 times 2 is 120, and 4 times 2 is 8, so that's 128. 64 times 2 is 128, so it'll be 1 and 1/28. All right, and we can go on and on doing the calculations by hand or just enter them in the calculator. We're not as concerned with the basic arithmetic, even though that is fundamentally important and is a foundation of algebra. Something that I think is more important right now is to get a grasp on the intuition and how negative power works. And again, if I have 2 squared, that equals 4. 2 times 2 is 4. That's what that means, is the power means 2 times 2. But 2 to the negative 2 power is just going to be the reciprocal, meaning flipping that fraction over, because 4 is really the rational number 4 over 1. So if we flip it over, 2 to the negative 2 power equals 1/4. So by that same logic, if I have for -1, then let's just remember what the power was for 1. When we had 1/2, if 1/2 to the 1 power. Anything to the 1 power is just itself. So if let me, here's another big word, axiomatic. That's a math word and it's used in other contexts, but it's meaning a kind of logic where you say, if this, then that. You can extrapolate, extend one idea to the next based off of an axiom where you've observed a kind of law. That's something you might run into in geometry next school year as they explore ideas from the Greek mathematician Euclid. He came up with a lot of those axioms. Anyway, you have, so if 1/2 to the 1 power equals 1, then 1/2 to the negative 1 power would just be flipping that over based on what we just went over. That would be 1/2 to the 1 power equals 1/2, because anything x to the 1 power just equals x. So 1/2 to the 1 power equals 1/2. So if we flip that over, then the 2 goes on top and the 1 goes on the bottom equals 2. And let me see if I can show you. Just pretend that there's a 1 underneath here. You don't see it, but it's actually 2/1. But 1/2 to the negative 1 power equals 2. And we're working with let me go back to my green. We have 1/2 to the negative 1 power, plus 1. So 1/2 to the negative 1 power equals 2. So 2 plus 1 would equal 3. And let's see what the spreadsheet thinks. And drag that formula up. Yes, it agrees with me that it's 3. So we have 3, and then can you guys guess what the next one would be for negative 2? So 1/2 squared was 1.25, because 1/2 squared is 1/4, and we're just adding 1. So you have 1/2 squared. Why did I put an equal sign there? 1/2 equals 1/4. 1/2 to the negative 2 power would just equal, flip that over, 4. And it's 4 plus 1, so it should be 5. So let me drag that up, if Excel will let me. 5, and then let's run through this a little bit faster. 3, 1/2 cubed is 1/8, so 1/2 to the negative 3 power would be flipping that 1/8 upside down, right? So it'd be 8, and it's 1/2 to x power plus 1, so 1/2 to the negative 3 power plus 1 would be 8 plus 1, which would equal 9. And then I didn't include it here, but by extension, we know, because I wrote it down over here for x equals 5, 1/2 to the 5th power plus 1 is 1 1/32. Well, we just flip that upside down, so that's 32. 1/32, the reciprocal of 1/32 is 32. 32 plus 1 is 33. So, that'd be negative 5. So 1 to the negative 5 power would be 33, but let's focus on 4. 1 to the 1/2 to the 4th power plus 1 was 1 1/16. Flip that upside down, that's 16 plus 1 is 17. So we'd go from 9 to 17 and then to 33. So the y value, as the x values get further and further towards negative infinity, the y values are going higher and higher towards positive infinity. So they're getting bigger as the x values move further and further to the left, away from 0 towards negative infinity. The y values, the output is going up, 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 in exponentially so because it's an exponential function. But what's happening in the other direction? Well, in the other direction, and I'll show you guys a graph of this in 2 different platforms, but I'm just going to drag this formula down, down, all the way to 48, and I'll go back up. You see that it's rounding everything to 1, but let's make sure that we take advantage of this key. Okay. So you notice all these numbers that were 1, you see a lot of zeros here, and that's because, you know, we can only round so much on Excel, but it's never actually going to reach 1. It's just becoming a smaller and smaller number that's closer and closer to 1. And let's show you a little graph. There's going to be a better graph that you can see in Desmos than what the spreadsheet on Excel will show for this example. But there's one facet you'll see on the Excel spreadsheet that I think will be helpful once again in informing your intuition. I have to hold down the control key on Excel, by the way, to be able to highlight 2 different columns. And I'm going to go to Insert, and then over here for Charts. And I like it where this one, where it's showing this graph, where it's showing the line and the dots. You get a similar idea with the bubbles. But you notice in both cases on this graph that it's, as we go further and further toward, as we get larger and larger x values, each output is closer and closer to the previous output and to the next output. So they're lumping together, and the reason is because they're getting closer and closer to 1. But they're not achieving it, and so that's why I'm going to show you on Desmos that you can really appreciate that here, because you can actually zoom in. You can't really zoom in on that on the graph on Excel. It's more static, and this is more dynamic, meaning dynamic is like fluid, like water running through a bathtub, whereas static is like a photograph. It's something that already took place. There's nothing you can do to change it. It's not an ongoing process. With the Desmos, you can zoom in and you can zoom out where it looks like it achieves 1, but again, as we zoom in, we never actually get to 1. It's just getting closer and closer, and that would be the definition of an asymptote. So let's go back to a Word doc. For the asymptote, it's going to be y equals, it's a horizontal asymptote, but y equals 1. So it never, problem 8, I think. We're up to, we did a little bit of this on the previous video, but asymptote is y equals 1. And you could also abbreviate that as H for horizontal, A, horizontal asymptote, 8, or again, y equals 8, which would mean that we have, let's zoom in. It's typically an asymptote, it's typically drawn as a dashed line. So you have this dashed line that we never actually cross, and then to try and graph that, because you can't really zoom in and this is all very static. If this wasn't the era of COVID and you turn this in for like a test, let's say, anything like this would be fine. For my purposes, I think the stellar thing is to appreciate that it never actually reaches 1. Speaking of which, when we write our range, we can think of it as range, because it can go as high as positive infinity, but we never get below 1, and it would be in parentheses because we never reach it. So the range would be from 1, as low as we can go, going down, as far down as we can go, is almost 1. So parentheses 1 to infinity. And domain, there's no restriction on what we can enter for the domain, so it's all real numbers. And the vertex, there really isn't a vertex. It'd be tempting maybe to pick this area where the y-intercept is, but it's not really two lines converging. So none. X-intercept. This graph doesn't even reach 1. It never goes below 1 on this horizontal asymptote. 1 is right above the x-axis, so it never crosses the x-axis. So no, there is no x-intercept, none. Y-intercept, well, it crosses it, as we were stating, anything to the 0 power equals 1, and 1/2 to the 0 power was 1, but it's 1/2 to the 0 power plus 1, so it's 1 plus 1 equals 2. So the y-intercept is at y equals 2. Y equals 2. It's also the ordered pair 0, 2, but y equals 2 is sufficient. Increasing, well, again, just like you read from left to right, as we increase each input, each output is getting smaller and smaller and eventually is approaching 1 but never reaches 1. So there's never really a point where this graph is increasing, so none. And then decreasing, well, yeah, as each x value, each input gets larger or moves to the right, each y value keeps getting smaller and smaller. At a certain point, it becomes infinitesimally small, which is a concept in calculus, and that's why they're doing this to you, is they want to get you guys ready for some of the intuition you would need when and if you ever take calculus, but also a really good idea to understand on an abstract level when you're writing and doing other things. But I digress. For decreasing, we are at between negative infinity and it's decreasing as each x value goes from negative infinity to positive infinity, because we can still continue, because the domain is all real numbers. So as we move to the right from leaving negative infinity going towards positive infinity, this thing is decreasing the whole way. It's just decreasing by a smaller and smaller fraction each time. Each slice is thinner than the previous slice, but it's still decreasing. And that's all there was. That is problem 7 in as exhaustive of a fashion as I can possibly give it to you, present it to you if you were at all struggling with problem 7. Problem 8 and 9 are relatively simple, so I'll do those in one video that will be much, much shorter.